Now, in this video, we're going to look at how to tackle more complex rational expressions and converting them into power series. And the way that we're going to do that is by looking at derivatives of our original geometric series formula. So let's look at our original formula. We've got a over 1 minus x, and that's equal to our power series. Now, I'm going to rewrite this to make my taking derivatives a little bit easier. As a times 1 minus x to the negative 1. So I can apply my power rule. And so that is my first round of formulas. But the more complex ones I can get from taking the derivative of these formulas. So the derivative of this function, I would have my a, I bring down a 1, I would get another 1 from doing the chain rule. And so these ones are going to cancel, and I'm going to end up with a over 1 minus x quantities squared. And on this side of the expression, I'm going to apply my derivative as well, also a power rule, and my x to the n is going to become n x to the n minus 1. Now, one thing to keep in mind when you're doing these derivatives, when n is 0, this entire term is a constant because it's a times 1. And so every time you take a derivative, you're going to lose a term in your sum. So if it started at 0 before, it's going to start at 1 the next time. And each time you take a derivative, this is going to keep happening. If we do our second derivative, then I had my previous negative 1 and 1. But now I'm going to bring down a negative 2 and another negative from the chain rule. And so this is going to end up being 2a over 1 minus 3 to the whole denominator cubed. When I take my derivative of the sum, again, I lose another term at the start, but now I bring down my n minus 1 from my power rule, and my power of x comes down to n minus 2. And I can keep doing this for as long as it goes. What I essentially end up with as I keep doing this is I'm going to end up with k factorial for however many derivatives I take. I'm going to end up with a 1 from the first derivative, and a 2 will survive from the second derivative, and then a 3 will survive from the third derivative, and a 4 from the fourth derivative, and so forth, times whatever my initial a value was. And then my denominator will be 1 minus x to the negative k plus 1. So it was negative 1 to start with. When there's no derivatives, when there's one derivative, this is going to be 1 plus 1, which is going to give me negative 2. And then my second derivative is going to give me 2 plus 1, which is going to be negative 3, and so forth. And then my summation formula, n minus 1, n minus 2, blah, 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 all the way out, one of these factors for each derivative. And then actually this will be n minus k plus 1. And then, because it's 1 less than this. And then my exponent will be n minus k. So 1 subtraction for each derivative that I take. Now, in most cases, and I should just caution this, in most cases, you're not really going to see textbook problems that go past these first two derivatives. So this generic formula, you don't really have to worry about it. You can always just retake these derivatives. But typically, I have seen some examples where we go to the third derivative, but in most cases, if you are asked to do these kinds of things, it's only going to be the first and second derivatives. If you can do it for one derivative in principle, that means that you can do it for others. Now, how do these formulas work? So in one sense, what we're going to do is we're going to end up rewriting these so that they start at 0 again. And we'll do that as we do the problems. So let's look at an example. So I want to find a power series for a function like this. And it looks like our previous power series, except that the denominator is cubed. And if the entire denominator is cubed, that means that we can't use the regular power series. This is corresponding to our second derivative formula from before. So that's this one, which simplifies to 2a over 1 minus x, or 1 minus r to the -3. And then this is our derivative that it's still starting at n equals 2 instead of n equals 0, but this is the point of our derivative process where we're starting. So we start with this side of the equation. We have to identify what a is, and we have to identify what r is. And so in this expression, 5x is going to be our r. But since our numerator is equal to 2a in this formula, then we set 4 equal to 2a. And so we get a is equal to 2. So kind of keep that in mind. And another way that you can do this is to actually just divide this 2 to the other side of the equation. That's fine as well. And then you don't have to worry about it. You can just plug in the value of the numerator into your formula and then go from there. It will cancel appropriately. Either way is fine. Now, once you have your formula plugged in with you've identified your a and you've identified your x, you're going to have to reset this formula at n equals 0. So here I've plugged in my a is 2 and my 5 to the n is going to be raised to 5 to the n minus 2 and x to the n minus 2 in both cases. And then my formula was n and n minus 1 in our sort of original derived case. Now, what we're going to do from here in order to get this to start at n equals 0 is, if I started at n equals 2 before and I plugged in an n here, if I plug in an n equals 0 here, I need my same expression, my corresponding expression in n, to give me the same value that it would have had before, which was 2. And so I'm going to add n plus 2 here. So that when I plug in n equals 2 here, I get a 2. And when I plug in n equals 0 here, I still also get a 2. So essentially, if I take 2 away from this, I have to add them back into the formula. Same thing for n minus 1. Here, if I plugged in a 2, I would get a 1. And here, I need to get a 1 if I plug in a 0. So again, I shift it up by 2. And so I get an n plus 1. And then my exponents, adding 2 back in, I get 5 to the n and x to the n, because when n was 2 here, and 2 minus 2 is 0. This is starting at 0, 5 to the 0. That's right. Same thing for x. The a, of course, doesn't depend on n, and so it stays the way that it is. And then from this point, then I can continue finding the formula for the derivative, finding the interval of convergence, sorry. And then for a second example, in this case, we have our function here. We have a negative sign that we're going to have to pull out of the denominator for our r. This is to the 4th power, so this would be that third derivative formula. And then our a now is also going to depend on x. So we're going to have a little bit of extra algebra simplifying to do. And again, we can do the simplifying before or after we do the shift. It's not, in the end, it's not going to make any difference. But our formula that we derive from above, 3 factorial is 6, because it's 3 times 2 times 1. So this is 6a over 1 minus r to the 4th. Our r in our denominator is going to be negative 3x to the 5th. And a, if we move the 3 factorial over to the other side of the equation, then a is just our 7x squared. If we don't move it over, we would set our 6a equal to this, And then we would get that 6 on the other side because a would be 7/6 x squared. But we're going to get the same thing here. Now, the one thing that we're then going to have to do is we are going to have to apply our shift. So once we get our formula all set up and simplified, our 7x squared is going to have to be combined with our x to the, so notice here, this is x to the 5th, but it's being raised to the n minus 3 power. So x to the 5n minus 3 power. The x squared is going to have to be added to that. So this will be 15n or 5n minus 15. Add the 2, you get 5n minus 13. And we still have our n minus 1, n minus 2. If I want to start this again at 0, then I'm going to need to add 3 to everywhere that I have an n in this problem. So n minus 1 plus 3 would become n plus 2. And for the alternating, that's just going to be -1 to the n plus 2 is just the same as -1 to the n because it goes back and forth. This 3n minus 4 would become 3n minus 4 plus 3. And so it would become 3 minus 1. This n would become n plus 3. This n minus 1 would become n plus 2. This n minus 2 would become n plus 1. And then this one, I would replace n with n plus 3. And then I should get n plus 2, that would make sense. If I had done this shift earlier, I would have ended up here with 5n plus 2 would have given me 5n plus 2. Now, once you have the expression rewritten, then you can go ahead and you can do all kinds of additional work on it. If you wanted to find the antiderivative, for instance, the antiderivative of the original expression is kind of a mess. So it would involve chain rules and power and quotient rules and everything. Once we have an expression, though, we can actually do this antiderivative fairly straightforwardly. We would find the plus c generally by some value of the original function, or typically it's 0. We would get some other q for that. Finally, we could also do derivatives of this, also antiderivatives. I would not want to do an antiderivative of this original expression at all. That would be quite a pain. But I can easily come up with a power rule expression for this. Once I have the power rule converted, then doing the antiderivative, as we saw with the arctangent function, is quite straightforward. So you do run into this occasionally. Some books don't do very much with this. Some books will approach these kinds of problems in a slightly different way, but they end up with the same answer, just getting to it by a slightly different route. But these can be powerful and useful processes, and so it's worth knowing that they exist. Although, as I said, even when they do show up in most textbooks, it's only involving 1 or 2 derivatives, and they don't really go as far as these third and higher derivatives.